So just before the video starts here, guys, a couple of times I mentioned the voltage trace for the injector, and this, the red trace here is a voltage trace. This is an image I captured sometime in the past on my car. There is a current ramp for the injector and the voltage trace. You can see the flyback spike as the current is cut off. The magnetic field for the injector actually collapses and induces this distinctive spike that some of you guys will be well familiar with. You can see there is two distinct points on both of these traces that are synonymous with pintle movement. Here the pintle is opening on the current ramp. You can see this little artifact here, as they call it. That sounds a bit silly to me, but I don't want to call it an anomaly because it's completely normal. There the pintle is actually opening, and on the voltage trace, here's the pintle hump. That is the pintle actually returning under spring bias back to the closed position. These 2 points here, delta T between these 2 points, is the injector open time, not to be confused with injector on time, guys. They're two different things. Anyway, I mentioned this in context before the video starts because I do mention the voltage trace. So when you're looking at the current ramp, when the injector is actually being driven by the injector balance test set there, guys, you'll notice there is a hump on the downslope of the current ramp as well. But if you look at this trace, which was actually taken from a vehicle, in reality, you won't see that. That's why I do not mention it in the video, because you will not see it as far as on-vehicle testing is concerned. It is present there, but it's only really a function of the test set. You won't see it on vehicle. Okay, so on the bench here, guys, I've got a wee test set up, to actually demonstrate current ramp on an injector. I don't really know why, but I keep getting these oscillations that are coming from a current clamp here. That's cheap hand tech current clamp. Watch, I'll turn it off. You'll see them disappear. So those oscillations, as I said on the waveform, are strictly as limitations of my cheap current clamp. Okay, so I'll ask you to ignore those actually on the trace, although they're difficult to do. So I think I can still make the point that I'm trying to make in this video. So what I have here, guys, is just this is basically for injector balance testing. What it does is it pulses the injector. You can select a number of different modes, but I've just got it in continuous mode at the moment. So this is just set up as analogous to the in-vehicle setup, of course. I don't have multiple injectors. I have a single injector here. So we're monitoring the current to this single injector, right? So I'm going to actuate it. You'll hear it. I've got the trigger set up so it'll hold the waveform. And again, please ignore those oscillations that you see that are extremely annoying and somewhat undermine the clarity of the video here. 200 millivolts, the scaling, the amplitude scaling, and the time base I've got here is 20 milliseconds, guys. That's 20 milliseconds for the entire screen, okay? Snap-on actually shows you as an entire screen, so there's 10 divisions there, so it's 2 milliseconds per division if your scope operates like that. Okay, so my point to this video is it's critical that you actually develop an eye for the nuances in a trace, guys, right? And again, my apologies for the oscillations, which somewhat undermine this, but imagine this to be smooth, the line smooth. I've put the filter on, didn't help. But imagine this as just a standard current ramp trace that you would get from an injector. It'd be minus these oscillations here, right? But you can see the current ramp, so it's no shooting straight up, which is synonymous with no short in the windings for the injector. And you can see it ramps up, hits basically its plateaus, and then actually as it's turned off, ramps back down. There is one key element in this that some of you will definitely be aware of, guys, right? Let me actually render the injector inoperative off camera here. You'll certainly hear the change. So tell me, is that injector still being pulsed? that looks like it's still being pulsed, right? We can still see a current ramp. But did you notice any change in it? On the leading edge ramp, not so much the trailing edge, guys, right? Let me bring it back online again here. Can you see the subtle difference there? There's one thing that is disappearing clearly from the trace if you know where you look for it, guys. Now, you can hear the injector is still being pulsed there. You can't hear it anymore because the pintle is not moving, right? I've got a strong magnet on here that's actually holding the pintle in place. When I remove it, the pintle starts to operate again and it returns to a somewhat normal trace here, minus my oscillations, again, that I'm asking for forgiveness from. Right here, guys, right? What this is on the current ramp, on the up ramp here, this portion here, you can see there is a definite distortion in the ramp. What that is the pintle actually moving within the bore of the injector. Now, I think most of you guys, or at least some of you will certainly know that, of course, the injector is an electromagnet, yeah? You apply a pulse to the windings in the injector, forms a magnetic field, and that field is coming and going. That's how you're actually getting the pintle to actually move within the bore. On a current ramp trace for an injector, that anomaly in the up ramp here is the pintle actually moving. So what you have here is a ferrous piece of material, has to be, of course, to be affected by the magnetics. The ferrous material, the pintle itself, moving within the field. So the pintle itself will have its own magnetic field. So you have a field moving within a field. And what you have here is basically Lenz's law at work. Basically, when that pintle moves, that field will oppose the current that actually formed the field in the first place. I don't want to get too heavy into the physics definitions of it, guys, but that's basically what you're actually seeing. So again, let me render the injector inoperative by holding the pintle stationary. And you can see the little pintle hump, not to be confused with the voltage trace pintle hump. This is a current ramp pintle hump. It's gone. Why? Because the pintle's not moving. Yes, the rig is still simulating your engine control module. It is still pulsing the injector. Hence, we still have a live trace here. You can see it is a live trace, I think. I hope you can see that on screen, guys. And you think, well, you see that and you think, oh, it's good, right? You know, it's the injector's good. And it's not good. A pintle that's not moving or seized within the bore is not going to let any fuel flow. I suspect some of you will say, well, of course, that'll be obvious. You can hear the injector. Can you? I've been under hoods that the exhaust leaks have been so loud you can't hear a damn thing. Nothing, right? Plus, are you going to be able to distinguish this injector from the injector which might be a few inches away from it? Assuming it's going to be a multi-cylinder engine you're talking about. So, it's critical, guys, that you develop an eye for wee details like this. This is because the pintle is moving within the injector bore. The pintle itself will develop a magnetic field. That magnetic field is interacting with the field of the injector itself and actually momentarily opposing the current here, right? If you have an injector that's seized in the bore, it's contaminated with, or perhaps the car's been fallow for extended periods of time and it's seized in the bore, you know, corrosion or schmutz in the bore of any kind, particulate of any kind that has seized the pintle from moving in the bore, you're not going to have that distinctive pintle hump on the current trace. Now keep in mind, guys, this is the current trace. I've showed you guys in the past, maybe I'll put it up here, injector waveforms that are the voltage trace, right? This is the current trace, hence the somewhat struggling current clamp that I have. Perhaps it's time for a new one. That looks like there's some filtering going on that's missing within the current clamp itself. I think the Hall effect in there that actually measures the current needs to be switched in order to function, and I suspect there's some bleed into the signal going on there, but I don't know that for a fact. That's just a little more than a guess, to be quite honest, guys, right? So let me get the injector going again there. Again, it's obvious for us here, guys, but if you had multiple injectors, it might not be obvious. The engine's running, a lot of clattering going on, a lot of noise, deafening atmosphere or surroundings that you're actually working in the shop or whatever. You might not be able to hear it, but you should be able to make that distinction on that trace. And in a good current, on a good current clamp, it's that much more distinctive, guys. This is difficult to see because of the issues I'm having with my wee cheap current clamp here. As I said, perhaps time for another one. Okay, I'll leave it at that, guys. I hope that made some sense. I'll just close by mentioning this book once again, guys. Automotive Oscilloscope Waveform Analysis by Graham Stokes. Fantastic book. All the details are in here with respect to the test I just conducted. In fact, there's the page right there. It tells you the equipment, the setup, and what you're actually looking at. I really can't recommend this book enough. There's the ISBN if you're interested. That's it, boys. Cheers.